Hey guys, Rosie here with another video of computer science, and today we're going to be covering the topic of hexadecimal. Alright, so last time we did binary, and hexadecimal is yet another counting system, but we'll get into that in just a little bit, alright? So, you know, thinking about what is it? Okay, hexadecimal, alright? So you remember binary, obviously it counts in base 2, and we had denary, which counts in base 10. We've also got another thing called octal, which counts in base 8, which is something we'll get onto a little bit later, but not in this video. But hexadecimal is basically another counting system that counts in base 16. Alright, so, anyways, the first thing we should look at is denary, alright? So how does denary work, alright? So we all know that when we count with our normal hands, 0 equals 0, 1 equals 1, 2 equals 2, 3, and so on and so forth. And we end up with these numbers, alright? So 9 equals 9, so basically we all know how that works. So to understand hexadecimal, which I did this in the binary video as well, so if you haven't watched that, you should probably go watch it, but you don't have to, because I'm going to cover it from the start. But I'm going to basically teach you how to count, alright? You'll know how to count, but do you truly know how to count, alright? You need to think of it from a different perspective, and then try and implement that into another type of method, so you can actually learn to count in base 16. Alright, so you see here we've got our regular columns. We've got the ones column, the tens column, the hundreds column, and the thousands column, alright? So, ones is 10 to the power of 0, because anything to the power of 0 is always 1. 10 to the power of 1 is 10. 10 to the power of 2, so squared, would be 100. And 10 cubed would also be 1,000, right? So, obviously, since we're counting in base 10, we can use all these digits, right? We can use 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Obviously, when we go up to 10, we add 1 to the next column. So the way we're going to do this is we're actually going to go and add, we're going to come up with a number, so we're going to go with, I don't know, let's say 45, right? So random number. I'm going to pull up a calculator. We don't really need a calculator for this, but it's always useful to have one handy. All right. So the way we do this, right, is we look at it. All right. So how many times does 1,000 go into 45? All right. We're always going to use rounded numbers, okay? But it doesn't go into it any time. So if we put the calculator through it, obviously you already know this. So we go 45 divided by 1,000. Nothing happens. It's like 0.045. So we just place a little 0 in this column. Right? So obviously, if we were doing binary, this class is 4 bits, but we're counting base 10. Okay, so next thing we're going to have is we're going to do how many hundreds go into 45. Again, that's none. How many tens go into it? Well, we know for the fact if we divide 45 by 10, we're going to get 4 of them. Okay, and then if we look at this, how many 45? How many? Let me start again. Sorry. Right. So since 4 tens go into 40. All right, so what we need to do is we need to go 45 minus 4 times 10, all right? And that's going to leave us with 5, all right? Okay, because, obviously 4 times 10 is 40, 45 minus 40 equals 5, all right? So how many ones go into 5? 5 of them, right? So we end up with a number 45. Okay, do another one. We'll do, I don't know, 6, 4, 5, 7, all right? So the way we do this is we obviously need to reset this. So obviously, how many thousands go into 6,457? We know 6 of them go in there, all right? So we need to do 6,457 minus 6 times 1,000, 6,000. And that's going to leave us with 457. How many hundreds? Well, we know 4 of them go into it. Okay, so we need to then do 457 minus 4 times 100. And that will leave us with the number 57. Then we go, how many tens? We know 5 of them go into it. So 57 minus 5 times 10. That leaves us 7. And then obviously we know 7 ones go into that. So we ended up with the number 6, 4, 5, 7. All right. And that is what the example we got. All right. So now we need to move on to hexadecimal, obviously, because we already know how to count. We know how to count, but it's a matter of how we look at the way we do this, all right? So that's denary done. Okay, so now we need to move on to hexadecimal. So obviously, with hexadecimal, there's a certain notation we like to use. Whenever we see a hexadecimal number, the programmers tend to use 0x to notify that, and it's kind of like the universal standard. So if you ever see this, and then a bunch of either letters and numbers after it, then you know that you're normally most likely to be looking at a hexadecimal number. Okay, so you need to remember 0x, that means you will be looking at a hexadecimal number. So you could have 0x222, that's a hexadecimal number. That's the way it's notified. Alright, so how do we count past 9, obviously, because we know, obviously, you know, if you go back to this over here, you know, we already know these symbols, obviously, we know these symbols, so 0 is a symbol, you need to think of that as just, it's just a little diagram, a picture, per se, which will equivalent to nothing. And then this little symbol here, which obviously stands for 1, doesn't it? Okay, so, but obviously, have you ever seen anything that counts to 16? I don't think so. Unless you already know hexadecimal, then why the hell are you watching this video? Okay, unless you want to refine what you're looking at. Okay, so 0, okay, so we need to understand that this still means nothing, alright? 1 still means 1, same for 2, 3, 4, 5, 6, 7, 8, 9. So they all stand for what they normally stand for, but obviously we need to think about the number 10, 11, 12, 13, 14, and I need to add one more, 15. Okay. So obviously it's base 16. So we do actually have 16 symbols here. Obviously, you know, you always got to remember factor in 0, so that always counts to 1. That's why we count to 15. Right, so 0. So 15 minus 0 would be 15, but obviously we have 16 symbols here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. So obviously, how are we going to represent 10 as a symbol? All right. So we need to think about this, right? So 10 would be equal to A. We need to extend this column a little bit here, because we actually use the alphabet, all right? So A would represent 10, B would represent 11, C would represent 12, D would represent 13, E 14, and F would be 15. Okay, so that's how we represent those numbers. Okay, so we should probably go look at an example. This is one I did earlier just to make sure the system I was using will work again. All right. Okay, so if you're just ignore this for now, all right, that's not there. Just imagine I'm going to bring that all the way down just so it's not in the way of what we're doing here. Okay. But, okay, so you see here that since we're doing base 16, we, rather than having powers of 10, like over here, you know, we use powers of 10, we actually use powers of 16, all right? So we have 16 to the power of 0, which would be our 1s, 16 to the power of 1, which would be 16s, 16 to the power of 2, which is squared, would be 256s, 16 to the power of 3 would be 4096s, and then down here, obviously, we've got 16 to the power of 4, which would be 65536, all right? So, obviously, we're using 4 bits here, okay? So, the way that we need to look at this is if we type in an example, we type, I don't know, 658, alright? So, that's just a random number I picked at random. So now let's try and convert it into a hexadecimal number. So the way we need to think about doing this is we actually need to do basically what we did over here, alright? So we start with our most significant bit, alright? So that is 4096, alright? So we start with the bit that is going to be larger, so one larger than the number we've entered in, which is in denary. Alright, so we want to represent 658 in hex. Okay, so how many 4096 go into it? None at all, okay? We need to look at that. How many 256s? Well, I know for a fact that 256 is 512, right? So if we mark this out, 658, and we divide it by 256, it's going to come out with 2 point something, right? 2.57, right? We don't really care about this remainder here. We're always going to just like knock off the decimal as if it isn't there, all right? So we're going to place in the number 2, all right? So now we need to do 658 minus 2 times 16. Sorry, not 16, 2 times 256, because it's 16 squared. All right? Whoops, didn't mean to do that. All right? And you see here, if we go 658 minus 2 times 256, then we end up with 146, all right? And that is the next number we're going to start on. So we're going to ignore 658, we need to continue going through this, all right? How many 16s go into 146? Well, if we divide by 16, it's going to leave us with decimal. It's going to leave us 9, all right? So 9 goes in there, all right? So now we need to do 146 minus 9 times 16. And that's going to leave us with, if we go into here, so 146 minus 9 times 16 is equal to 2. Alright, so leave us with 2. Okay? And, okay, so obviously we've got 2 left, right? So obviously this is the ones column, we just put enter the number 2 simply, right? And then that is it. That is our hexadecimal number. And I can prove this, alright? So, thankfully, Windows 10 comes with a little handy-dandy updated calculator app, right? So, what we need to do is, if you see here, our final notation in hex for the number 658 would be 292, right? So that would be the hexadecimal notation for that, apart from if we're using it in a program, we'd have the number 0x, but we've stated that this number is hexadecimal, right? So if we open up the programmer on the calculator and we enter the number 658, you'll see here the hex value here is actually 292, right? And you can see that obviously since we switched to hex mode, it's going to show us all the little notations we can use for that as well. So hexadecimal shows that we can have the number represent the number, the denary number, which is in decimal, 658 as 292 in hex. All right. So let's also do this again. Okay. So let's use it another example. We'll do the number, I don't know, 7843. I don't know, something like that. Okay. So the way we do this is we need to reset this. So how many 4086 go into that? We know that one of them does at least. So obviously let's reopen up the calculator because it closed like a dumbass. So if we actually go 7843 and then we divide by 4096, equivalents to, oh, I'm in the programming mode, I need to change back to standard. So 7843 and we divide by 4096, comes to 1 point something. It's almost 2, but not quite. Because 2 times 4096 would be 8192, so 8192. But obviously we just want to focus on this. So if we do come into here and we go 7843 minus 1 times 4096, that is going to leave us with, so 7843 minus 4096, 3747, right? So now we need to think about how many 256s go into it. So we want to divide by 256. Comes up to 14.63, blah, blah, blah. So we have, so since we have the number 14, right, we don't actually use a regular number anymore. What we actually use is so if we come back to here, you see the number 14 is equivalent, is represented by the letter E. So we just input E into here to represent 14. So then what we need to do is we need to do 3747 minus 14 times 256. Okay, so E represents 14, right? Because remember, that's what we showed inside of here. You know, that's the symbol we use to represent that. Okay, so we need to do 3747 minus 14 times 256. Leaves us with 163, all right? So how many 16s go into that? No, we just divide it by 16. Comes up to 10 point something. Okay, so the 10 is represented by the symbol A. So we input A into here. And obviously, you know, we need to then proceed to do 163 minus 10 times 16, which obviously 10 times 16 is 160, so it leaves us with number 3. And then we just enter 3 into there, because that's that ones column, right? Because that's all we're left with. Okay, so that is how we represent the number. That's how we represent the decimal number 7,843 in hex, would be 1EA3. I can prove this if we open up the calculator and we go into programmer and we go into decimal mode and we go 7843. You see, hex would be 1EA3, which is what we have here. And that, my friends, is actually how we do hexadecimal. But, okay, what I actually want to show off here is, little trick for if you get given an easy number, right? And you might think easy, you know, obviously these are very, very large numbers, all right? You know, how can it ever be easy? So if you're ever given a value that's just f, that just consists of f's, all right? Make sure you write your little column headings. It helps a lot, all right? So this is the maximum value we can store under these column headings, all right? So you know that this is the maximum value. If we go into here, and we click hexadecimal, all right, and we erase all of that like that, all right, and we want to enter the value f. So we need 4 f's, 1, 2, 3, 4. You see the number we're given is 65,535, right? That's our decimal number. So click that, you know, 65,535. Wait a minute. You see over here, 16 to the power of 4 is 65,536. This is one less. So always write out a column heading before the column heading that comes after the maximum value you have. All right, and this will always equate to one less. All right, guys. That's it. You now know how to count in hexadecimal. But obviously, we want to look at, you know, like, why do we use it? What is it used for? So why do we use hexadecimal? And that's what we need to think about. So the reason we use it is it's just a simple representation of binary numbers. Okay, and so like what would normally be like 4 bits. All right, so 4 bits. So say we had 1111, which would be equal to 15. All right, we can just simply go, all right, you know, f is equal to 15, and it simplifies it so much. So when we're trying to show large values, and like an example of when we show a large value is when it comes to colors, because obviously colors are like infinitely large, right? There's an infinite number of them basically, because we can't exactly notify. There's always something in between, like, I don't know, blue and a lighter shade of blue. There's always something in between there. So if we have 32-bit color, obviously, you know, what would be shown as, you know, 32 bits in binary. So you know you've got 4 there. So what we show as 32 bits would be 4, 8, 16, 34, 8, 12, 16, and then 16 times 2. What would normally be shown, like a color, if we had 32 bits of color, would be shown like that, right? We can just simply simplify it down to a quarter, so it would be something like, this would be F, 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 F. So this here is equal to that, all right? And we can show that I can prove this again. If we open up the calculator, since it's literally a quarter of the size, so 1, 2, 3, okay, quarter of the size. So if we go and input the number in hexadecimal, 1, 2, 3, 4, 1, 2, 3, 4. You see here we've got 1, 2, 3, 4, 5, 6, 7, 8 groups of binary numbers. So you got 1, 2, 4, 5, 6, 7, 8 groups of binary numbers there. So it's very useful for when we represent in 32-bit of color, stuff like that. Alright guys, thanks for watching. This has been Grovesy. I hope you now understand how we represent hexadecimal numbers. And yeah, I hope it helps. I'll catch you guys in the next one. Bye.